In Lecture 6b, we will learn to compute a Pearson product moment correlation coefficient, use correlation coefficients to assess reliability, common variance, and effect size, and identify situations in which the Pearson R does not accurately reflect the degree of the relationship. The Pearson correlation coefficient measures the linear strength of the relationship between two variables. Here are a couple of the different ways to calculate the value for R. In the blanched formula, you need to have the means and standard deviations for both of the two variables that you have. The raw score formula, you just need to be able to find the sums of the x and y values, the x squared, y squared values, and of the product xy. I gotta be honest with you though, this calculation is definitely getting into the land of ridiculous in terms of doing it by hand. I worked several of them for the concept checks, and I've decided that it's time for us to just switch to Excel for this type of stuff. There's just too many places where you could end up making a transposition error or, forgetting one zero in one number, and it could just turn into a nightmare. So I'm going to show you how to use Excel to calculate the values for R. And there's lots of different ways to do that, so we'll start off with one where I show you how to use the raw score formula. Okay, I'm going to show you how to use Excel here to calculate the value of the Pearson correlation coefficient, and I'm going to do this example using the raw score formula. There are many different ways that you could do this, but this one I think is the one that's probably the most accessible in terms of if you had to do this by hand. Alright, so to do the raw score formula, I'm going to set up a table here for my values that I'm going to need in the formula itself. And I see that if I make a list, I'm going to need n, I'm going to need the sum of xy, the sum of x, the sum of y, and the sum of x squared, and the sum of y squared. So I'm just going to set that up in a logical form up here. So I have x, y, and x squared, and y squared, and then the product of x times y. And on this, I'm using the data from our bird colonies plot from Lecture 6a. And remember, for this one, we wanted to be able to predict the new adults. So that means that the new adults belong in the y column, and the percent returning belongs in the x. Okay, now all I'm going to do is let Excel do the work here. To get the values of x squared, I'm going to go equals, click on the first x value, and then to say squared, you use Shift 6, that little caret key, and then a 2 for squared. So what it just did is it did 74 times 74. Now, to make this happen easily, I'm just going to select that first cell, drag down, and then I'm going to fill down. You can just go Control D. There are other ways to do it. I'll try and show you a couple of them as we go through. Alright, so now this last cell is 38 times 38, or 1444. Y squared, same game, equals, click, and caret 2 for squared, and then fill down. Actually, let me try to show you this way. Fill down, do you see this little guy right there? Go down and it fills. So if you just take that little box, that also does a fill down. And now for xy, it equals this cell multiplied by the y value that it's paired with. And then we'll fill down again using that little box. Nope. There we go. Alright, now I want to find the sums for each of these columns. So I'm just going to say equals sum parentheses and then highlight my column. And this time I want to fill right, so I'm going to grab and go to the right with it. And it just did all the sums for us. Very easy. I'm going to boldface these so that we don't accidentally, actually I'll change their color too, just so that it's really obvious that those are the sums and not part of our original data set. Okay, now for this hairy formula. I know it looks gross, but it's really not that bad. First off, what is our n? Our n is 13. There are 13 pairs of data. Okay. Now what I want to do for calculating r is I'm just going to do one big equation. All right. And I have to make sure of a couple of things. So I have to make sure that my numerator, the one on top, stays separate from my denominator. So I'm going to start off with an equals and a parentheses. That parentheses will encapsulate the entire numerator for this thing. All right. Now n was 13. I'm just going to type that one in. I could have done it as a cell, but 13's easy. 13 times the sum of x, y. That's this one right here. Okay? Minus the sum of x times the sum of y. Okay? I'm going to close that parenthesis because I'm done with the numerator. Now I'm going to divide, and for this bottom one I see I've got two sets of subtractions separated and multiplied, plus a square root thing. So I'm actually going to end up needing two parentheses, and I'll show you why here as we go. N, so I'm right here, n is 13, and I want the sum of x squared multiplied by the sum of x squared. There we go. And then I want to subtract the sum of x quantity squared. So I'm subtracting this. Here's the sum of x, but I want to square that sum. The difference between sum of x squared and the sum of x quantity squared. Okay? So that's so far as this first, all the way up until the square. All right, I'm going to close this first parenthesis. See how it's color coding it for me? And I'm going to now multiply it by the second set of parentheses. So I'm going to get n, 13, times the sum of y squared is the only one up here we haven't used yet. Okay, minus the sum of y quantity squared. Here's the sum of y, and I want to square that quantity. I'm going to end this parentheses. You see how I still have green parenthesis to green parenthesis, so I have one more parenthesis left because I want this all to be on the bottom. There we go. See how it bolded that one? Bottom of my fraction, and I still have to do the square root. Now, you may remember this from high school math, but the square root is the same thing as raising to the half a power. So that's how I like to do it in Excel, just because it's nice and clean and I don't have to use a SQRT like text to type in. So if you need to take the square root, use the 0.5. So everything should be set now, so when I hit return I should get, well, let's see, I should get a negative number because I know as I have high values of percent returning paired with low values of new adults. So I'm expecting a negative number. And from our graph that we drew before, I expect it to be kind of a moderate range. So let's see what happens. Yep, negative, and it's moderate to strong, it looks like, in terms of the strength of this relationship. So this value right here is the Pearson correlation. Okay, graph that so you can see it. Excellent, and that's it. That's all we had to do using Excel. It's a heck of a lot easier than, you know, doing this all by hand. But it's still, you have to be kind of careful. This formula that we used up here, right? You just got to be very slow and deliberate about making sure that that you get all little parts of it. Okay? Using Excel to calculate an R. One of the nice characteristics of the Pearson value for R is that it's got this extra property when it is called R squared. It's the coefficient of determination. And what it represents is how much of the variable x is shared in common with the variable y. And it's often referred to as their percent of shared variance. One of the things about this is it kind of tempers your enthusiasm for really high values of R, because one way to interpret this R squared coefficient of determination is that it's a way for you to say, well, it's the likelihood that if I were to use X to predict Y, how often I would end up being accurate in those predictions. So if you have an R, say, of 0.8, so that's really very, very strong for an R. 0.8 times 0.8 is 0.64, which means that you could interpret it as only 64% of the two variables are shared in their variances, or you could say only about 64%, or maybe 2/3, you could round a bit, 2/3 of your predictions would actually be accurate for Y based on X. There are two instances in which there may be a really strong relationship present between two variables, but it doesn't show up in a value of R that represents strength. The first case would be where you have a nonlinear relationship. In this example, we're plotting anxiety on the x-axis and performance on the y-axis. The idea being that if you have a moderate amount of anxiety, it actually kind of acts as a stimulant to bring your performance levels up. But if you have too low or too high, your performance levels are down. So it forms this nonlinear shape. You would get a very, very low value for R if you tried to calculate it, because remember, R only works for linear relationships. The other example where you could have a pretty strong relationship, but it doesn't show up, is if you were to truncate a range. So in this example, I have X and Y as my variables, and if you look at the entire graph, you see that the R for that entire thing is about 0.9, and that's very strong. But if you were to just isolate the topmost range of the X values, and just look at the part of the graph there that is circled up, it looks like in that particular case, the R is essentially 0, because those dots have a radial appearance. Now, this is called a spuriously low correlation because it's not really true. It's not really what the big whole picture is. To get that whole picture, you need to look at the entire range of the data, right? Not just one little segment of it.